Measurements and Matter, Chapter 1. The objectives in this chapter include 1. The scientific method, 2. Measurements, 3. Numbers, 4. Units, 5. Dimensional analysis, 6. Matter and its classifications, and 7. Physical and chemical properties and changes. Your goals. By the end of this chapter, you should be able to apply the scientific method, take measurements correctly, work problems out using dimensional analysis. This is how we're going to show our work. Classify matter, identify physical and chemical properties and changes, and differentiate matter as either a pure substance or a mixture, and then place them in their appropriate categories. 1. The scientific method. The scientific method is a cyclic process where information is gathered via observation, explanations are formulated, and then tested with experiments. The components include observation, hypothesis, experimentation, conclusion, and then we can draw up scientific laws and theories. Observations. Observations are a statement that accurately describes something one senses. We may use our sense of sight, touch, hearing, taste, or smell. Observations themselves may be qualitative. For example, the water in the beaker is hot. Or quantitative, one may take the measurement of the temperature of the water in the beaker and it's 99.8 degrees Celsius. A hypothesis is a tentative explanation to observations and laws. A good hypothesis may be revised. Experimentation itself is highly controlled observations, and the observations made are referred to as data. A conclusion is a statement that is based on what is thought of a series of observations. Scientific law is a broad generalization made after many observations. For example, the law of conservation of matter states that matter may change form during a chemical reaction, but the amount of matter is conserved. All of the reactants must end up in the product. They just can't disappear. Scientific theory is a well-tested explanation of the behavior of nature. A scientific theory is a deeper and broader explanation to the observations and may be altered as experimentation continues. For example, the law of conservation of matter indicates that matter is neither created nor destroyed in a chemical reaction, but it may change form. We can therefore predict that if we start with 500 grams of reagents, we should end up with 500 grams of products. The why to the law of conservation of matter was explained by early scientists with Dalton's atomic theory. We will learn the currently accepted scientific theories that explains the why. Make sure to apply the scientific method to your studies. 2. Measurements. Measurements are part of experimentation. Various instruments may be used. It is important to learn how to use the instruments and record values and units. Digital instruments. Whenever you are working with a digital instrument, you always record all the numbers on the screen or the display, and of course the unit. The numbers that are recorded are all the certain digits and the one uncertain digit. The certain digits are all the digits before the last one on the screen. The uncertain digit is the last digit on the screen. What should you record? Hopefully you said everything. 16.43 grams. We will also use graduated instruments. When we use graduated instruments, make sure to always record one decimal place past or to the right the smallest increment or tick mark. The numbers that we record are all the certain digits, which are the digits read including the digit based on the smallest increment, and the uncertain digit. The uncertain digit is one decimal place past the smallest increment that you must estimate as accurately as possible. Whenever you use graduated instruments, like this graduated cylinder here, you must take a look at what the smallest incrementation is. So let's go ahead and take a look at this graduated cylinder. It goes by ones. Ones is our smallest increment. So for example, here's 5, here's 6, 7, 8, 9, 10, and so forth. That means we can record the volume of the liquid in the graduated cylinder to the ones place with certainty. So we have 20 right here. Here's 20, and then 21. So we know 21 is going to be our two certain digits, the 2 and the 1. We cannot stop here though. We have to record that one uncertain digit. We have to guess this as accurately as possible. So note, we're going to make the reading at the bottom of the meniscus, and it looks like a 0.6. So 0.6 will be our uncertain digit. With this instrument, we have to record to the tens place because it goes by ones. So what do we think the volume should be? Hopefully we think about 21.6 mLs. Make sure that you always look at what the smallest increment any graduated instrument is going by and record 1 decimal place past that smallest incrementation. Measurements and significant figures. A measurement always contains all the certain digits plus 1 uncertain digit. These are also known as significant figures or sig figs. Significant figures come from taking a measurement correctly. When we work out problems, the values given are assumed to be measurements taken correctly. We recorded a mass, 16.43 grams, and a volume, 21.6 mLs, correctly. So how many sig figs? We just count them. 1, 6, 4, and 3, that's 4 digits, so it has 4 significant figures. 21.6, 2, 1, and 6, that's 3. Therefore, there are 3 significant figures in that measurement. Make sure that you're able to record the number of significant figures correctly based on the instrument you are working with. When we take measurements, there might be some calculations that we need to apply to those measurements. Some common measurement calculations include percent yield. That's how much product is obtained compared to the calculated or predicted quantity. You should know what the percent yield equation is. Percent yield is equal to the actual yield, that's going to be what is collected in the laboratory setting, divided by the theoretical yield, or how much product can be made using up the limiting reactant, times 100%. Ideally, the percent yield for a given reaction is high. We may also take a look at the accuracy or correctness of our values. This has to do with how close an experimental or average value is to the ideal value. If we take an average, that means mean, we may need to do an extra calculation before we can determine accuracy. To take an average, we need to add up all of our data values and divide it by the number of data points in that given set. To then determine accuracy, we measure the percent error. Percent error is the experimental value or the average value subtracted from the ideal or true or accepted value. Then we divide that difference by the ideal value times 100%. The percent error ideally will be a low percent error, and that will then give us information in terms of accuracy that our experimental or average value is very accurate if the percent error is low. Continuing with common measurement calculations. We may also want to determine the precision or reproducibility of our data. That just means how close the experimental values are to each other. In order to determine the precision, we can calculate the standard deviation lowercase s. We will be doing these calculations in lab, but let's go ahead and go over the equation here. The equation to determine the standard deviation, beginning with the numerator, we need to take an individual value xi and subtract it from the average, or x bar. Once we have the difference, we square that difference. We will do that same calculation for every individual value. Individual value minus average. Once we have the difference, we square it. Then we will add, that's what the summation symbol here means, we will add all of the answers or all of the squares of our differences. That takes care of the numerator. In our denominator, we're going to take the number of trials or number of data points minus 1. Once we have that number, we're going to divide both the numerator by the denominator. Then we take our answer and we take the square root of that. That will give us the standard deviation. It's a little bit tricky to see whether or not the standard deviation value is a good value or a poor value. So oftentimes we may calculate the relative standard deviation, or the RSD. The relative standard deviation is obtained by taking the standard deviation S and dividing it by the average value, or X bar. Then we multiply by 100%. If the values are very close to each other, the relative standard deviation will be very, very low. But if they're far apart from each other, then it will be high. So the lower the relative standard deviation, the more precise the measurements are, the better. Errors. Errors may occur when one makes observations or conducts an experiment. There are two types of errors, systematic and random. Systematic error occurs when the experimental values are all higher or all lower than the actual value. This is either due to faulty instruments or consistent mistake in reading by the experimenter. We must avoid systematic error because it is preventable. The other type of error is random error. The experimental values are both higher and lower than the actual value. The magnitude of the random error depends on the instrument's precision and the experimenter's skill. Random errors will always occur, but may be minimized. Students then must learn how to avoid making systematic errors and to minimize making random errors. We need to ensure that we take measurements correctly. We will use digital and graduated instruments. Avoid systematic error by using the calibrated tools appropriately, and then minimize random error through practice.
3. Numbers. There are rules for determining the number of significant figures in a given value or a measurement. The first rule regards non-zero digits. All non-zero digits are significant. If we consider a value like 3.9, it has how many sig figs? Well, the 3 and the 9 are both non-zero digits, so they're both significant, and therefore it's going to have 2 sig figs. The next set of rules correspond to interior zeros, trailing zeros, leading zeros, and zeros at the end of a number. Let's start with interior or sandwich zeros. If we have zeros in between significant figures, then the zeros in between are significant. Therefore, 9802 has how many sig figs? Well, it's going to have 4 significant figures because the 9, the 8, and the 2 are non-zero digits, and the 0 is in the middle. Trailing zeros are zeros after a non-zero digit and after a decimal point. Those are significant. If we consider a number like 19.770, it has to have 5 sig figs because the 1, the 9, the 7, and the 7 are significant, and the 0 at the end is after non-zero digits and after a decimal point. It does not need to be right after, it just has to be after. Now we get to zeros that are not significant. Leading zeros, or zeros in front of the first non-zero digit, are not significant. These are placeholder zeros and they serve only to locate the decimal. Therefore, 0.0058 has only 2 sig figs, the 5 and the 8, because the zeros in front are in front of the first non-zero digit, the 5. Zeros at the end of a number and no decimal point are not significant because they are ambiguous. So if we have a number like 460, the 4 and the 6 are significant, so there's 2, but the 0 at the end is not because it's ambiguous. We need to use scientific notation to make it very clear which zeros are significant when we have scenarios like the last one. Make sure that you're able to tell the number of significant figures in a given value or in a measurement, and note where the last significant figure is at. In our first example, the 9 is in the tenths place. In the second example, it's in the ones place, the 2. The 0 is in the thousands place in our third example. Our last sig fig is the 8 in our fourth example, and in our very last example, the 6 is in the tens place. There are ways to write numbers. The two ways that we use are decimal notation and scientific notation. 205.3 is written in decimal notation. It has 4 significant figures. The 2, the 5, and 3 are non-zero digits, and the 0 is sandwiched in between, therefore it is significant. 2.00 times 10 to the 7 is written in scientific notation. Whenever we have numbers written in scientific notation, the decimal portion of the number is all significant. So 2.00 has 3 sig figs, and it's times 10 to the 7th. Make sure that you practice using your calculator to go in between the two notations.
Converting to scientific notation by hand. Consider converting 635,200 into scientific notation. The first thing you want to do is to locate the decimal point. When it's not written, it should be in the default spot between the ones place and the tens place. 2. Move the decimal point to the left until there's only one non-zero digit in front of the decimal point. Make sure to count how many times you move the decimal. 3. The number of times the decimal was moved is a value of the exponent, n. 4. Because the decimal was moved to the left, n is positive. For example, let's go ahead and follow the steps. We want to first locate the decimal and then move it to the left. We have moved it over 5 times. We're going to write 6.352 times 10 to the positive 5th. Now, in both notations, the number of sig figs should be the same. We have 4 sig figs in the given value and 4 sig figs in our scientific notation value. They mean the same thing. If we have a positive n, that means that we're multiplying the decimal part, 6.352 times 10, 5 times. So our value, 6.352 times 10 to the 5th, is 6.352 times 10 times 10 times 10 times 10 times 10, giving us 635,200. In both methods of writing the same value, the number of significant figures must remain the same. What if we have a number that is less than 1? Consider converting 0.000888 into scientific notation. The first step is the same as before. Locate the decimal point. The second step, we're going to move the decimal point this time to the right until there is one non-zero digit in front of the decimal point. Make sure to count how many times you move the decimal. 3. The number of times the decimal was moved is the value of our exponent, n. 4. Because the decimal was moved to the right, n is going to be negative. For example, our value, if we locate our decimal and then move it to the right, we're moving it 1, 2, 3, 4 times. So our value should be 8.88 times 10 to the negative 4. And both are going to have how many sig figs? Hopefully we all agree with 3. 3 significant figures. Now our value represents a calculation, 8.88 divided by n 10 times. That's what the negative value is telling us. So 8.88 times 10 to the negative 4 means 8.88 divided by 10 times 10 times 10 times 10, or 0.000888. We should also be able to go from scientific notation to decimal notation using both our calculators and doing it by hand. When we are converting a number from scientific notation to decimal notation, the first thing we want to do is to look at the exponent n to determine the number of times to move the decimal. And we're going to move the decimal to the right if n is positive. So 6.352 times 10 to the 5th is telling us that we have to move the decimal over 5 times and to the right. When we do so, we have to put in the zeros as needed, and we end up with 635,200. The same number, but in decimal notation. We have to move the decimal to the left if n is negative. So 8.88 times 10 to the negative 4 will require us to move the decimal to the left 4 times. And we have to put in zeros each time we have a movement that does not have a number. So now we have our value 0.000888, which is the same as 8.88 times 10 to the negative 4. We need to add zeros. We saw that in both cases as needed. Exact numbers. Exact numbers are values that have an infinite number of significant figures. It is because they have no uncertain digit. There are three sources of exact numbers that you must know. The first source of exact numbers is counting of objects. The second is defined quantities. There are a few exceptions to this. And the third are integral numbers of equations. For example, if we count the number of pennies, there are 3 pennies. The number 3, because it's associated to pennies, has not one sig fig, but an infinite number of sig figs because there's exactly 3 pennies. The relationship between feet and inches is also an exact relationship. 1 foot is exactly 12 inches. That means that the number 1 and the number 12 both have an infinite number of significant figures. When a defined quantity is not exact, I will let you know. And if we consider the equation r equals, or the radius equals, the diameter, or d, divided in half or divided by 2, that number 2 does not have one sig fig. It has an infinite number of sig figs because we would divide the diameter exactly by 2. These are the 3 sources of exact numbers. If the value you are working with is not from one of these sources, it will have a finite number of significant figures. If we have calculations, there are different rules for sig figs and calculations. Before the rules though, make sure to memorize the rules and apply them correctly. The output on your calculator is a result of your input. Make sure the answer makes sense. Calculators do not know sig fig rules and will usually display too many digits or not enough digits. You need to use the rules to decide how many sig figs your answer should have at the end and to what decimal place. Let's go ahead and begin with multiplication and division. The rule: the answer that you have should have the same number of significant figures as the factor with the least number of significant figures. If you need to round the number, follow rounding rules. For example, if we are trying to multiply 7.1 by 5.44, we are going to see 38.624. Because our first factor has 2 sig figs, while our second factor has 3 sig figs, our answer has to stop with 2 sig figs. Because the 6 after the 8 is greater than or equal to 5, we're going to go ahead and round up the 8 to a 9. Our answer is 39. Let's go ahead and continue with addition and subtraction. The rule: the answer should stop at the same decimal place as a term that goes to the right the least in terms of its last sig fig. In other words, we need to look at the decimal place of the last significant figure in all of our terms. Let's go ahead and practice. If we are adding 9.2 to 771.34, we need to look at the location of the last sig fig. We're not counting them. In our first term, the last sig fig is the 2, and it's in the tenths place. In our second term, the last sig fig is the 4, and it's in the hundredths place. Since the tenths goes to the right the least and the hundredths, our answer, 780.54, is going to be rounded to the tenths place, or 780.5. We're going to keep the 5 as a 5 because the number that came right next to the 5 was a 4, so we leave our value as is. Let's review our decimal places. The last decimal place of a number recorded will vary depending on the instrument used. We need to stop with the first uncertain digit. We will also need to know the location for addition and subtraction rules. In the previous example, we were working with two terms. One term ended in the tens place and the other ended in the hundredth place. Notice that the tens place goes to the right the least. We may have terms that end in the ones place, the tens, the hundreds, the thousands, 10,000s, 100,000, million. We can keep on going, and we can also go in the other direction. When we add or subtract, we're paying attention to the location, the decimal place of our last sig fig. Whichever one goes to the right the least, or whichever one stops first, that's the value that we're going to go ahead and base our last sig fig in, either our sum or our difference. Rules for sig figs and calculations. If we have multiple steps, follow the mathematical order of operation rules. At each step, keep in mind the sig fig rule and track what the outcome would be if one would stop at that point, round at the very end. For example, if we were going to take 1.5788 times 2.991, in our numerator, that first operation is multiplication. We care about which value has the least number of sig figs. Our first value has 1, 2, 3, 4, 5. Our second value has 1, 2, 3, 4. So our answer, if we only did this calculation, would have 4 sig figs, or we would stop at that second 2, 4.722. I'm going to keep all the digits on my calculator until I'm done with the calculations. In my denominator, the operation is subtraction. With subtraction, we care about where the last sig fig is at. In our first term, the last significant figure is the 2, and it stops at the tens place. In our second term, our last sig fig is a 4, and it stops in the ones place. When we take the difference, 177.2 minus 114, we get 63.2 on our calculators, but we know, based on the operation, our last significant figure would be in the ones place. Now for the last operation. We are dividing. Dividing, we care about how many sig figs we have. In our numerator, we would have 1, 2, 3, 4. In our denominator, stopping in the ones place, we would have 1, 2. So our answer needs to have 2 sig figs. When we divide our two values, we end up with 0.074718, etc. Because we need 2 sig figs, we're going to keep 0.07, and we're going to round up the 4 to a 5 because the next number is a 7. Remember that all the zeros in front of our first non-zero digit are not significant. So 0.0 are not significant digits, but the 7 and the 5 are. The numbers in measurements. Values have significant figures. Those are all the certain digits and the one uncertain digit where we stop. Be able to count the sig figs for multiplication and division. Be able to identify the decimal location of the last sig fig and a value for addition and subtraction. Exact numbers have an infinite number of sig figs and will not limit us in calculations. Be able to use decimal and scientific notation to write numbers. 4 units. There are many systems of units. The system commonly used in the United States is known as the English system. The English system has units, for example, of length that corresponds to inches, feet, yards, miles, of mass or weight, ton, pounds, ounces. Please note that mass and weight may be used interchangeably here on Earth. However, mass and weight are not the same thing. We know that the amount of matter is mass, while weight is a function of matter interacting with Earth's gravitational pull. The system that is used, though, by most of the world and the sciences is the International System of Units, or SI units. This is based on the metric system. We will primarily be using the SI unit system. Derived units are units that are formed by combining other units, for example, area and volume. Let's go over the SI units. Make sure that you know Table 1.1. If the quantity we want to measure is length, the SI unit is the meter, and the symbol is lowercase m. A common instrument that is used to measure length is a ruler. If we want to measure mass, the SI unit is kilogram, and the symbol is lowercase k, lowercase g. The g is telling us its mass. And the common instrument used is a balance. The SI unit for time is second, with the symbol lowercase s. We may use clocks or stopwatches as instruments to measure time. The SI unit for temperature is Kelvin. The symbol is uppercase K, and the common instruments that we use to measure temperature in degrees Celsius or degrees Fahrenheit is a thermometer. The amount of matter is measured using the unit of mole, and the symbol is MOL. We oftentimes obtain the number of moles of substances calculated from masses. Electric current, we use ampere with the symbol A, and the common instrument for electric current is a multimeter. The SI unit for volume is the cubic meter. The symbol is m to the third power. Common instruments that we may use include graduated glassware like graduated cylinders. Let's consider length. Make sure that you know that the SI unit for length is the meter. The length relationship between English and the metric system, since we might need to convert between the two, is that 1 inch is exactly 2.54 centimeters. The relationship between inches and feet, 12 inches are equivalent to 1 foot. Make sure that you know. For mass, the SI unit is the kilogram or lowercase k, lowercase g. But the base unit that tells us this is mass is gram, lowercase g. The relationship between the systems includes that 1 kilogram is equivalent to 2.205 pounds. There are other relationships that will be provided for you if necessary. For time, the SI unit was second, lowercase s, and we know that 1 minute is 60 seconds, 1 hour is 60 minutes, 24 hours are in a day. For temperature, the SI unit is Kelvin, uppercase K. There are other temperature scales that we use quite frequently, degrees Celsius and degrees Fahrenheit. For the amount of matter, the SI unit is moles or MOL, and 1 mole of anything corresponds to 6.022 times 10 to the 23rd anything. We also know this number as Avogadro's number. For volume, we saw it's a measure of space, and we use the SI unit cubic meters or meters to the third power. We oftentimes, though, use liter or uppercase L in chemistry. 1 liter is equivalent to 1 times 10 to the negative 3 cubic meters, and 1 milliliter is equivalent to 1 cubic centimeter. Prefix multipliers. Prefix multipliers change the value of the unit by powers of 10, are applied to any of the SI units, and are used in conjunction with dimensional analysis. Why would we use prefix multipliers? Well, a wide range of measurements may be expressed in more appropriate units. One may choose a prefix multiplier which is most convenient for a particular measurement. For example, if we are traveling, we may use kilometers instead of meters. One can convert from a given unit to a desired unit using dimensional analysis if we're involving prefix multipliers. Let's consider the prefix multipliers. Make sure that you know this table. If we have the prefix tera, the symbol for tera is uppercase T, and 1 tera anything corresponds to a trillion anything, or 1 times 10 to the 12. If we have giga, 1 giga, which is uppercase G as its symbol, represents a billion anything, or 1 times 10 to the 9. Mega. If we have a mega anything, the symbol is uppercase M, and 1 mega corresponds to a million anything, or 1 times 10 to the 6. Kilo has a symbol lowercase k. If we have 1 kilo, that corresponds to 1,000, or 1 times 10 to the 3rd. Deci has a symbol lowercase d. If we have 1 deci anything, that corresponds to 0.1, or 1 times 10 to the negative 1 of that anything. Centi has a symbol lowercase c. If we have 1 centi anything, that's 1 times 10 to the negative 2. Milli has a symbol lowercase m. This is the second time that we have seen lowercase m. In this case, when we see it, it should be a prefix in front of any of our base units. 1 milli anything is 1 times 10 to the negative 3 of that anything. Micro has a symbol lowercase mu. 1 mu corresponds to 1 times 10 to the negative 6. Nano has a symbol lowercase n, and 1 nano corresponds to 1 times 10 to the negative 9. Pico has the symbol lowercase p, and 1 pico means 1 times 10 to the negative 12. And femto. Femto has the symbol lowercase f. 1 femto corresponds to 1 times 10 to the negative 15. Make sure that you know these prefix multipliers. Conversion factors setup practice. Let's say we're going to compare terameters to meters. The first thing we want to do is write our equivalency statement that reflects a relationship. 1 terameter equals 1 times 10 to the 12 meters. We get the relationship 1 tera equals 1 times 10 to the 12 from the table that we have memorized. To set up our conversion factors then, we put 1 terameter in the numerator, and then we can divide that by 1 times 10 to the 12 meters in the denominator. Or we can flip it. We could put 1 times 10 to the 12 meters in the numerator, and at the bottom we can put 1 terameter. The one that we use depends on the given and the find information. Let's do another one. If we're comparing kilograms to grams, the relationship between kilos and the base unit is 1 kilo equals 1 times 10 to the 3rd, or 1,000. So 1 kilogram equals 1,000 grams. Set up your 2 possible conversion factors. Well, we could put 1 kilogram on top and 1 times 10 to the 3rd grams at the bottom, or we could flip it. We could put 1 times 10 to the 3rd grams on top and 1 kilogram at the bottom. The one that we use depends on the given and the find. Let's say we're comparing milliliters to liters. We would get the relationship again from our memory bank or the table that 1 milli equals 1 times 10 to the negative 3, or 1 milliliter equals 1 times 10 to the negative 3 liters. We can put the 1 milliliter on top and the 1 times 10 to the negative 3 liters at the bottom, or we can flip the ratio. 1 times 10 to the negative 3 liters on top and 1 milliliter at the bottom. Let's do one more. If we're comparing nanometers to meters, the relationship between the two is that 1 nanometer equals 1 times 10 to the negative 9 meters. We can put the 1 nanometer on top, the 1 times 10 to the negative 9 meters at the bottom, or we can flip it. We can put the 1 times 10 to the negative 9 meters on top and the 1 nanometer at the bottom. The one that we use depends on our given and our find information. Density. Density is an extensive property of matter. It is used to tell matter apart. Make sure that you know the density of water and, of course, the density equation. The density equation equals the mass of the substance over the volume of the substance. Table 1.3 gives us a selection of densities. Here's table 1.3. Here are the different substances. It's a limited list. And this is the densities of each of those substances in grams per milliliter. Make sure that you know the water's density is 1.00 grams per ml. In other words, for every 1 gram of water, it has a volume or space of 1 milliliter. Know this to 3 sig figs. Other density values will be given to you or it's what you're going to find based on the given information. Note the two metals in the example here, platinum and silver. They're both silvery metals, they're both solid, but they differ significantly in their densities, and we could use density to tell them apart. Platinum has a density of 21.4 grams per ml, while silver has a density of 10.5 grams per ml. We would want to do other analysis to conclude that these are silver and platinum, but the densities are a quick way to determine that they're not the same thing. Now let's determine density. The density equation is density equals mass over volume. Recall that this sideways slash here really means a horizontal line. So density is equal to the mass of our substance over the volume of our substance. For example, a substance was found to have a mass of 38.771 grams and a volume of 15.42 mLs. Let's find the density. We'll identify what's given to us. The mass is given to us, 38.771 grams, and the volume is given to us, 15.42 milliliters. We're trying to find density, which we know means mass over volume, in this case, grams over milliliters. We're going to use the density equation. That density is equal to mass over the volume. And we know then that we have to input our mass value on top, 38.771 grams. And at the bottom, we're going to input the volume, 15.42 milliliters. Since mass and volume are not exact numbers, or sources of exact numbers, the numerator has 5 sig figs, the denominator has 4 sig figs, so our answer at the end should end up with 4 significant figures. And we do to 2.514 grams per milliliter for our substance. We make sure that we have the correct number of significant figures in the number, and we have the correct units, grams per ml. Density as a conversion factor, example 1. Density relates mass and volume. Therefore, if we know density and we know mass, we're able to find volume by using density as a conversion factor. Or if we know volume and density, we can find mass, again, by using density as a conversion factor. Let's do an example. What is the mass of a 15.00 ml volume of ethanol if we have the density of ethanol as 0.789 grams per ml? Let's identify what's given, 15.00 mLs, and the density 0.789 grams per mL, and we want to find mass. Since we're not told what mass unit to go to, and density has a mass unit of grams, we're going to stop at grams. We want to view density as a conversion factor. Remember that that horizontal line is really represented here by the sideways slash, 0.789 grams over 1 milliliter. Or we can flip the ratio if we need to. 1 ml of ethanol has a mass of 0.789 grams. Once we decide which one of the two conversion factors to use, we're going to use the first one since it has mass on top. Then we can set up our work. Our solution map is going to relate milliliters to grams, and we're going to use density as our conversion factor. For every 15.00 mLs, we're going to determine what that mass corresponds to. So every 1 ml has a mass of 0.789 grams. The mLs cancels out, and we're left with 11.8 grams. So 15.00 mLs of ethanol will have a mass of 11.8 grams. In terms of significant figures, the density has 3 sig figs, the given volume has 4, so our answer has to have 3 sig figs. And of course, don't forget your unit. Density as a conversion factor, example 2. A gold bar has a mass of 0.985 kilograms. What is the volume in liters of the bar if the density of gold is 19.3 grams per cubic centimeter? The first thing we want to do is indicate the given and the find. The given information is the mass of gold, 0.985 kilograms, and the density, 19.3 grams per cubic centimeter. We want to find the volume. We know that density is what relates mass and volume, so we are going to use this as a conversion factor, except that the mass that we're given is in kilograms, so we have to convert kilograms to grams first. When we find the volume, we're going to find it in cubic centimeters, which means we have to convert this to milliliters before we can convert it to liters. Therefore, our solution map is going to be the following. We're going to take kilograms and convert that to grams using a prefix multiplier. We're going to convert our answer to cubic centimeter using density, then to mLs, and finally to liters. Let's go ahead and set up our conversion factors. We're going to start off at 0.985 kilograms. We're going to put our kilograms on the bottom and grams on top. For every 1 times 10 to the third grams, that's 1 kilogram. And then we're going to convert to volume by putting 19.3 grams at the bottom and 1 cubic centimeter on top. We're going to convert cubic centimeter to milliliters by recalling the relationship that it's 1 to 1. Finally, we're going to go ahead and convert milliliters to liters by using the prefix multiplier relationship, that 1 times 10 to the negative 3 liters is 1 ml. That results in 0.0510, 3 significant figures due to the given mass and the density. The other relationships are exact, and 3 sig figs is after all of our zeros in front. The 5, the 1, and the 0 at the end are significant. Our unit should be liters, and let's go back and see how all of our units cancel out. The kilograms cancel out with each other, the grams cancel out, the cubic centimeters cancel out, and the milliliters cancel out, leaving us with just liters. So our conversion factors were set up with logical flow, resulting in the volume that we were looking for. Temperature. Temperature is a measure of how hot or cold matter is. There are 3 temperature scales. One can compare the 3 scales with the boiling point and the freezing point of water as reference. In degrees Fahrenheit, water has a freezing point of 32 degrees Fahrenheit and a boiling point of 212 degrees Fahrenheit. In degrees Celsius, water freezes at 0 and boils at 100. In Kelvin, water has a freezing point of 273.15 Kelvin and a boiling point of 373.15. Temperature equations. Let's relate degrees Fahrenheit and degrees Celsius. We're going to consider the boiling point and freezing points of water using each scale and determine the difference in each scale. If we take the boiling point, 212 degrees Fahrenheit, minus the freezing point, 32 degrees Fahrenheit, we will get a range of 180 degrees Fahrenheit from the boiling point to the freezing point of water in degrees Fahrenheit. If we do the same calculation, but now in degrees Celsius, notice that 100 degrees Celsius minus 0 degrees Celsius is 100 degrees Celsius. That's the range of the freezing point and boiling point in degrees Celsius for water. If we divide those two values, the 180 degrees Fahrenheit by 100 degrees Celsius, we will get that 1.8 degrees Fahrenheit is equivalent to every 1 degree Celsius. And the scales are offset by 32 degrees Fahrenheit, so we need to add in that term. We will get that the temperature in degrees Fahrenheit is equal to 1.8 degrees Fahrenheit over 1 degree Celsius times the temperature in degrees Celsius plus 32 degrees Fahrenheit. Note that the constants 1.8 and 32 are exact. They have an infinite number of significant figures and will not limit you in calculations. It is common to use the equation with all of the units on the constants. So feel free to use the temperature in degrees Fahrenheit equals 1.8 times the temperature in degrees Celsius plus 32. We may need to rearrange this equation to solve for the temperature in degrees Celsius. To do so, we need to subtract 32 from both sides and then divide by 1.8. Make sure to take the difference first or put the difference in parentheses before we divide by the 1.8. Once we do so, we can solve for the temperature in degrees Celsius. Temperature equations relating Kelvin and degrees Celsius. There is an equation that allows one to convert between Kelvin and degrees Celsius units. With these scales, every degree Celsius is equivalent to 1 Kelvin, but the offset is 273.15. and that's going to result in the temperature in Kelvin is equal to 1 Kelvin per 1 degree Celsius times the temperature in degrees Celsius plus 273.15 Kelvin. It is common to also use this equation without the units on the constants. Therefore, you may use the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. Remember that the constant 273.15 is exact. That means it has an infinite number of significant figures. And the lowest possible temperature in Kelvin is 0 Kelvin, or absolute zero. You may also need to rearrange the equation to solve for the temperature in degrees Celsius if you're given the temperature in Kelvin. To do so, all we need to do is subtract 273.15 from both sides to obtain the temperature in degrees Celsius equals the temperature in Kelvin minus 273.15. Temperature conversions. Let's go ahead and practice converting between the different temperature units. Consider the boiling point of helium. It boils at 4 Kelvin. What is 4 Kelvin in degrees Celsius and degrees Fahrenheit? We're given 4 Kelvin. You want to find the temperature in degrees Celsius and degrees Fahrenheit. We're going to need to use the temperature equations that relate Kelvin and Celsius and Fahrenheit. The first equation needs to be rearranged. We need to take the temperature in Kelvin and subtract from it 273.15. That will give us the temperature in degrees Celsius. We just need to input then the 4 Kelvin minus 273.15, which will result in negative 269.15. Because our first term ends at the ones place, our answer needs to be rounded to the ones place as well. Therefore, in degrees Celsius, the temperature is negative 269 when helium boils. Now to convert this temperature to degrees Fahrenheit, we need to plug in our negative 269 degrees Celsius into the second equation. By plugging it in, we end up taking 1.8 times a negative 269, and then we add the 32. That will result in negative 452 degrees Fahrenheit. Make sure that you are able to convert between the temperature units with ease. Units give meaning to the number. We will use the SI system of units and the metric system, be able to convert between units using dimensional analysis. Always include units in your work, and don't forget to check your significant figures. 5. Dimensional analysis. Dimensional analysis is also known as the factor label method, and that refers to the use of units as a guide to solve problems. We will always need at least one equivalency statement. This indicates that 2 or more values are known to be equivalent. For example, we know that 1 foot is equivalent to 12 inches, and 1 centimeter is equivalent to 1 times 10 to the negative 2 meters. From the equivalency statement, we can then set up a conversion factor. So consider the 1 foot equals 12 inches. We may set the conversion factor where we have the ratio and the 1 foot on top of that ratio line, and at the bottom the 12 inches. Or we can flip it. We can put 12 inches on top and the 1 foot at the bottom. Let's consider the second equivalency. 1 centimeter equals 1 times 10 to the negative 2 meters. We can set up 2 conversion factors. We can put the 1 centimeter on top, the 1 times 10 to the negative 2 meters at the bottom, or we can flip our ratio where we put the 1 times 10 to the negative 2 meters on top and the 1 centimeter at the bottom. There is a dimensional analysis pattern that we want to make sure we follow when we set up our work. We will have to know what the relationship is between our given and our find unit in order for us to set up our conversion factor. Usually, our given unit and our given information is in the numerator. Therefore, our conversion factor should have it in the denominator in order for the given units to cancel out and the find unit to be left. Make sure the conversion factor that we make is from the equivalency statement that relates the given unit and the find unit. We treat the units algebraically. That is why they can cancel out if we have one on top and one at the bottom. They should cancel out, and we might have intermediates, by the way. Problem solving steps. Number 1, read the problem carefully. 2, identify the given values with units and the find unit. 3, make a map. Write down the solution map from the given unit to the find unit. Identify the equivalency statements between the units, or how are the units related. You will need at least one. If a problem involves a base unit, which is a unit with no prefix multiplier, then one conversion factor is needed. If the problem involves two prefixes, then usually two conversion factors are needed. Set up the problem or how you show your work. One needs at least one conversion factor, but some problems may require two or more. In general, our pattern will always be that we start off with our given and our given unit, and our conversion factors are set up so that the given unit can cancel out, and if we need to have intermediate units, those also will eventually cancel out until we are left with the find unit. Do the math. Make sure that your units cancel or stay like we saw earlier, and don't forget to check your significant figure. Let's practice with a length conversion. Consider the diameter of a poliovirus. It is found to be 2.87 times 10 to the negative 8 meters. What is this diameter in centimeters? We are given the diameter as 2.87 times 10 to the negative 8 meters, and we're trying to find that length in centimeters. We want to consider then what is our map. Our map should take us from meters to centimeters, and that means we have no prefix here and a prefix here, therefore one conversion factor. That means we need to know what the equivalency is between centimeters and meters. Using our prefix multiplier table, 1 centimeter is equal to 1 times 10 to the negative 2 meters. Once we have identified how the given and the find units are related to each other, then we can set up our work. We're going to put 2.87 times 10 to the negative 8 meters as our starting point, and then build from our equivalency statement our conversion factor, where we'll put 1 centimeter on top and 1 times 10 to the negative 2 meters at the bottom. That will allow the meter units to eventually cancel out, and we will end up with 2.87 times 10 to the negative 6 centimeters. And the units that we don't want should cancel out. Note that we have started off with a value that has 3 significant figures. The equivalency statement that we used is an exact relationship, therefore the conversion factor is exact. We do not have to worry about how many sig figs this has because it's infinite. We're multiplying and dividing, so our answer should end up with 3 sig figs, so 2.87, but in this case, don't forget, the times 10 to the negative 6. And of course, we finish up with our unit. Now let's consider a mass conversion. The mass of a 4-cylinder aluminum engine of a small modern car is 150.0 kilograms. Convert this mass to megagrams. We're going to identify our given and our find. We are given 150.0 kilograms, and we are told to find this mass in megagrams. Let's make our map. We want to convert between a prefix to another prefix. That usually means 2 conversion factors, and we need to go through the base. We know that the base, based on the second symbol, is a mass unit. So we're going to go from kilograms to grams, and then from grams to megagrams. We need 2 relationships, or 2 equivalency statements. The first one should relate the kilo to the base unit. 1 kilogram is 1 times 10 to the 3rd grams. And the second one should relate mega to the base unit. 1 megagram equals 1 times 10 to the 6 grams. Once we have identified our strategy, our map, and relationships that we need to use, now we can go ahead and set up our work. We start off with the 150.0 kilograms. We put 1 kilogram at the bottom, 1 times 10 to the 3rd grams on top. We then put 1 megagram on top and 1 times 10 to the 6 grams at the bottom in order to have our grams cancel out and our kilograms cancel out. we should be left with megagrams. We end up, when we plug this into our calculators, with 1.500 times 10 to the negative 1, or 0.1500. Note that our given value has 4 significant figures. Our conversion factors are exact, and we're multiplying and dividing, so our answer must also have 4 sig figs. Don't forget the unit, megagrams. And of course, go back and check that your units do cancel out with logical flow, and they do. Length conversions. Let's convert from English to metric. Consider paper. The length of a piece of paper was measured to be 11.01 inches. What is this length in centimeters? We are given 11.01 inches and we're told to find this in centimeters. Now, in both cases, the given and the find are length units, but one is the English system and one is the metric. So we need to know what the relationship is between inch and centimeter. In this case, there is a direct relationship, and that equivalency statement, or that relationship, is that for every 2.54 centimeters, that's 1 inch. We only need one conversion factor. We're going to start off with our given, 11.01 inches. We're going to put the 1 inch at the bottom because we want inches to cancel out, and the 2.5 centimeters on top since we're looking for that unit. We end up with 4 significant figures with 27.97 centimeters. Remember that the 2.54 centimeters in 1 inch is exact. Therefore, our 11.01 given value is going to limit us to 4 significant figures. Of course, make sure your units canceled out with logical flow. Wavelength conversion. The wavelength of a certain UV light is 247 nanometers. Convert the wavelength to micrometers. Go ahead and identify the given and the find. The given is 247 nanometers. The find is micrometers. Go ahead and determine your solution map. How do we get from nanometers to micrometers? Then determine the relationships that you need. Hopefully, our map goes from nanometers to the base unit meters and then to micrometers. We need 2 conversion factors or 2 relationships. The first relationship should convert 1 nanometer to meters. 1 nanometer is 1 times 10 to the negative 9 meters. And the second one should convert 1 micrometer to meters, or 1 micrometer is 1 times 10 to the negative 6 meters. Once we have the relationships, we are able to set up our work. Beginning with the 247 nanometers, set up your conversion factors. Hopefully, we wrote down 247 nanometers, and our first conversion factor, 1 nanometer at the bottom, 1 times 10 to the negative 9 meters on top. Our second conversion factor, 1 micrometer at the top, and 1 times 10 to the negative 6 meters at the bottom. When we plug this into our calculators and do the calculation to 3 significant figures, we should be getting 2.47 times 10 to the negative 1, or 0.247 micrometers. All the units that we don't want should cancel out. The nanometers cancel, and the meters cancel, leaving us with just our desired unit. The prefix multiplier conversions are exact quantities. Therefore, our given value is going to limit us to 3 significant figures because we're multiplying and dividing and it has the least number of sig figs. Using density as a conversion factor. Gasoline has a density of 0.65 grams per cubic centimeter. What is the mass of 500.0 liters of gasoline? Let's identify the given and the find. Given is the density of gasoline as 0.65 grams per cubic centimeter. Don't forget that we may view this sideways slash as a horizontal line where we have the mass on top and the volume at the bottom. We are also given the volume of gasoline as 500.0 liters. We are trying to find the mass of gasoline, and mass has units of grams because our density unit is in grams per cubic centimeter, so we're going to stop as soon as we hit grams. Let's determine our solution map. Well, we know that volume and mass of gas is going to be related via the density. So we are going to have to use density as a conversion factor. But since we're starting off in volume, we want to make sure we convert our liters to milliliters and then to cubic centimeters in order to get us eventually to grams. The equivalency statements that we need are three of them: milliliters to liters, milliliters to cubic centimeter, and then gram to cubic centimeter. Let's set up our work. If we start off with the 500.0 liters, the first conversion factor should have 1 times 10 to the negative 3 liters at the bottom and 1 ml on top. The second one should help us get from milliliters to cubic centimeter, 1 ml at the bottom, 1 cubic centimeter on top. And our last one should have density. We have cubic centimeter at the bottom and grams on top. That will allow us to then find our mass, once we plug this into our calculators, as 3.25 times 10 to the 5th grams. All the units we don't want should cancel out.
The answer should have 2 sig figs as 3.3 times 10 to the 5th grams.
Units raised to a power, area. Sometimes a problem requires that one solves for a unit to a power that is not in the set you have memorized. Not to worry. This just means that the equivalency statement, the conversion factor itself, must be raised to that power when you do the calculation. Let's consider a room having an area of 855 meters squared. What is the area in centimeters squared? We are given 855 square meters. We want to find the area in square centimeters. The map, well, we're going to take meters to centimeters, but we're going to have to square our conversion. The relationship between the length units, 1 centimeter, it's equal to 1 times 10 to the negative 2 meters. When we set this up into our conversion factor, we're just going to square our conversion factor so that we end up squaring everything, the numbers and the units. Let's write down 855 meters squared. Our conversion factor, 1 centimeter over 1 times 10 to the negative 2 meters. Note that the power of centimeter and meter would not cancel out yet. So we're going to go ahead and square our conversion factor. Once we do this, we're going to take 855 and divide by 1 times 10 to the negative 2 squared, which is 1 times 10 to the negative 4. That will result in 8.55 times 10 to the 6th centimeters squared. Then our units cancel out the logical flow. Units raised to a power, volume. Let's consider a cube that has space or a volume of 4.2 cubic meters. What is this volume in cubic inches? Let's go ahead and write down our given, 4.2 cubic meters, and our find, cubic inches. Our map. If we don't consider the cube, we know how to go between meters and centimeters, and then from centimeters to inches in length. Since we want volume, all we have to do is cube our relationships, the equivalency statements, the conversion factors. We're going to use 1 centimeter equals 1 times 10 to the negative 2 meters to help us go between meters and centimeters, and 1 inch equals 2.54 centimeters to go between centimeters and inches. However, we're going to have to cube each relationship. Let's start off with the 4.2 cubic meters. We're going to put 1 centimeter on top, 1 times 10 to the negative 2 meters at the bottom, but we're going to cube it. Then 1 inch on top, 2.54 centimeters at the bottom, but we're going to cube it. This will allow our length conversion factors to become volume conversion factors. When we plug this into our calculators, we should get 2.6 times 10 to the 5th inches cubed. The units that we don't want should cancel out with logical flow. Units raised to a power. An example. Sometimes we have to watch out that we don't raise conversion factors to a power because the ratio is already to the appropriate power. An example of this is the volume relationship that 1 ml is 1 cubic centimeter. Let's do an example problem. A nanobot has a volume of 1.95 times 10 to the 4th nanoliters. what is this volume in cubic meters? Well, we are given 1.95 times 10 to the fourth nanoliters. We are told to find cubic meters. We're going to have to convert our nanoliters to liters first in order for us to convert liters to milliliters. Once we're in milliliters, we know the relationship between milliliters and cubic centimeters. All of these conversions so far are all volume, but our last conversion to cubic meter, that is going to have to use a length relationship, which means we're going to have to cube that equivalency statement or that conversion factor. The relationships that we need are here below. 1 nanoliter is 1 times 10 to the negative 9 liters. 1 milliliter is 1 times 10 to the negative 3 liters. 1 ml equals 1 cubic centimeter. And then the length relationship, that 1 centimeter equals 1 times 10 to the negative 2 meters, but we're going to have to cube it. Let's go ahead and set up our work. Starting up with 1.95 times 10 to the fourth nanoliters, we're going to set up the first conversion factor by putting 1 nanoliter at the bottom, 1 times 10 to the negative 9 liters on top, and 1 ml on top, 1 times 10 to the negative 3 liters at the bottom, so that those units can cancel out eventually. Top 1 cubic centimeter, on top 1 ml at the bottom, 1 cubic centimeter. Eventually will be at the bottom, 1 times 10 to the negative 2 meters cube will be at the top once we cube the entire conversion factor. We should end up with 1.95 times 10 to the negative 8 cubic meters, and all the units we don't want should cancel out with logical flow. Six, matter and its classification. Matter may be classified by state. We may classify matter as a solid. The symbol is lowercase s in parentheses. In the solid state, particles are close together and the atomic molecular motion is about a fixed point. Solids have fixed volumes and shapes, but their hardness may vary. Solids may be crystalline. That just means the particles that make up that solid are arranged in a pattern, or amorphous, which means the particles are not arranged in a pattern. We also have the liquid state. The symbol is lowercase l in parentheses. Particles are close together, about as close as a solid particle would be, but are free to move around and by each other. Liquids have fixed volumes but not shapes. Liquids take the shape of their container and have an upper surface. Matter may also be classified as a gas. Gas has a symbol lowercase g in parentheses. Atoms or molecules in a gas are separated by large distances and are free to move relative to one another. Because of this, gases are compressible, and gases will assume the volume and the shape of their container. We will also see aqueous quite a bit. Aqueous has a symbol lowercase aq in parentheses. Aqueous represents a substance that's dissolved in water. Matter classification by composition. Matter may be classified as a pure substance. A pure substance can be an element. An element is a substance that cannot be broken down into simpler substances by chemical reactions. All the known elements are on the periodic table. An example of one is iron with the symbol Fe. A pure substance may also be a compound. A compound is one that is composed of two or more elements in fixed definite proportions or fixed ratios, and are said to be chemically united. In other words, they're going to have a chemical formula. Matter may also be composed of mixtures. Mixtures are composed of two or more different pure substances in variable proportions. A mixture may be homogeneous, which means it appears the same throughout, or heterogeneous, which means the appearance varies from one region to another. We are going to study all of these classifications. Number 7, physical and chemical properties and changes. Properties are characteristics of matter. There's physical properties, which means the chemical formula stays the same, and chemical properties, which means the chemical formula will change. Physical property examples include taste, odor, color, appearance, melting point, boiling point, density. Chemical properties include corrosiveness, acidity, flammability, toxicity.